It's just you here, Michael. When we talked last time, we were talking specifically about vectors, and we had gotten basically through the vector algebra stuff. So hopefully, if you have any questions of that, hopefully you got a good understanding of it. But if you still have questions, now's the time you can ask. Uh, However, at the end of that, I also started to get into kinematics and specifically talking about projectile motion. And the most important thing you can learn was from that diagram I showed you, where there was a red ball and a yellow ball, and they were both at the initially the same height. But the yellow ball was launched horizontally with some speed at the exact same instant the red ball was dropped. So when you look at that photograph, you'll see that at each point in time, the balls are exactly at the same height at each point in time. And that shows you that gravity acts the same on the ball, whether the ball is moving to the left, moving to the right, moving up, moving down, literally even moving up. Now, the difference is when it's moving up, obviously it's slowing the ball down, but it's slowing it down by a very consistent amount, just like it's speeding up the red ball that was dropped by a very consistent amount. For instance, every if you ignore air resistance, every second the ball will speed up going downward by 9.8 meters per second each second. That's why I told you guys to use the meters per second as meters per second when we talk about acceleration instead of meters per second squared. So if you actually drop a ball and if you allow it to fall for one whole second with no air resistance, then it'll go from 0 to 9.8 meters per second. And then if it falls another second, it's going to go another 9.8 meters per second. So that'd bring it to 19.6 meters per second, and so on and so forth. Now, the ball that was actually shot upward, its velocity is also going to change by that 9.8 meters per second. And notice the 9.8 was increasing going down. So when this ball has been thrown up, it's going to decrease its velocity by 9.80 meters per second each second it's in the air. If you wanted to zoom in on it and look at it per tenth of a second, then it's going to change its velocity by 0.980 meters per second every tenth of a second. So that's another way. But the main thing is to realize that that 9.8 meters per second each second is exactly how much the velocity is going to change each second, whether the ball is going to the right, to the left, up, or down. So oops, didn't mean my shirt be that be that unbuttoned. So once we have that in mind, we can solve problems a little easier. So what I thought I'd do is open up by or start up by working a single kinematics problem that has sort of nothing to do with projectile motion. So let me start with that just to give you an idea of exactly how to solve such a problem. And then that's going to come in handy when we go to try to study projectile motion. So I'm going to share my iPad screen. Okay, this should come up in a second, and I apologize. I did all this as my handwriting, and I did it just a few minutes ago, so it's not that clear. But it says, consider a ball thrown upward with an initial velocity of 30.00 meters per second. If it is thrown from a height of 1 meter, what will be the max height it reaches? How long will it take to get to that height? That's part B. Part C, how long will it take to return to its initial height? D, what will be its speed when it reaches its initial height? E, what will be its speed when it hits the ground? And F, how long will it take to hit the ground? So I've got a lot of different things going on there. We're trying to figure out if I throw a ball up with initial velocity of 30 meters per second, what is all these events that are going to transpire? So let me go ahead and write down what we know. Oops. I'm going to write down what we know, and actually I need to change my eraser to a smaller one. So solution. To do this solution, we need to write down what we've been given. What we've been given is that a ball is thrown upward with initial velocity of 30 meters per second. The symbol that corresponds to that is a velocity, so that'd be a v. Your book sometimes uses, and other books sometimes use the Greek letter nu, which looks just like v. So sometimes if you don't see the v looking like a v, that's why they're using the Greek letter nu. And then we subscripted 0, our I, for the initial, so that's 30.00 meters per second. And that's again me trying to remind you that when you take a test, if you can assign each of the values that were given to you or that were implied by the problem, if you can assign them to an appropriate symbol, then I can start giving you credit for that problem, even if you can't solve the rest of it. So make sure you always do that. We also know since it was thrown upward, and I didn't give you any more details, you must assume that it's on planet Earth, and you must also assume, since I didn't give you any details about air viscosity or anything like that, that they must want us to ignore air resistance. And because of that, that means our acceleration, since I called the initial velocity upward positive, that means anything pointing downward would be negative. Therefore, the acceleration must be negative g, which is negative 9.80 meters per second every second. So that's another piece of information we were given. Uh, it says for part A, they want to know uh, if it is thrown from a height of 1 meter, what will be the max height? So we know, for instance, y0 equals 1.00 meters. And what we want to know is what's its max height. So we want to know y max equals question mark. That's part A. Part B, it says, how long will it take to get to that height? So I'm going to say t at y max is equal to question mark. So notice I wrote t and then I subscripted it y max. So what I'm saying is, what is the time at which y reaches the y max height? And obviously, since I called it y, we're suggesting that the upward direction is the positive y axis. Part C, they're asking how long will it take to return to its initial height? So now we want to know t y0 equals question mark. And then part C, or excuse me, part D, it says what will be its speed when it reaches the initial height. So I'm going to say d v at t y0 is equal to question mark. In other words, at the time at which it reaches its initial height y0, what's the velocity at that point? Okay, so that's what part D is. And then part E says what will be its speed when it hits the ground. So we'll say part E, v at y equals 0 is the question mark, because now we're taking into account the fact that I launched the ball from initial height of 1 meter, and I'm trying to figure out once it goes all the way up, reaches its max height, and then comes right back by where I left it, which where I let go of it, which was at 1 meter. What then? How fast will it go just before it hits the ground? So that's what part E is. And then part F says, how long will it take to hit the ground? So in that case, what we're asking is really how long is it aloft? So I'm going to say F is T hang time. So that's just a phrase that we use, at least in sports, to say how long is it in the air. So that would be from the instant it left my hand, for instance, at the 1 meter mark. It reaches its max height and then it comes all the way back down. And just before it hits the ground, how long did that take? So that's all that we're trying to figure out here. Now, in order to do this, we need our kinematic equations. And one of the kinematic equations that we'll need is y equals 1 half at squared plus v0 yt plus y0. And another one we'll need is vy is equal to v0 y plus a sub y t, like that. And I could put the subscript y on the a as well, just to remind us that we're talking about the acceleration in the y direction. Those two equations are usually enough, but we also might use v squared is equal to v0 squared plus 2a. In this case, we might subscript the y, in which case this will be a sub y, and this would be y minus y0 instead of x minus x0. So those are some of the kinematic equations that we'll probably use. I'm going to start off with part A. Part A, we want to know how long it will take to reach its max height. The thing to understand here is when the ball is thrown up, it's going to be moving at 30 meters per second. And then after 1 second, it's going to be moving at 30 minus 9.8, which of course would be 20.2 meters per second. And then after another second, it's going to subtract another 9.8. And then after another second, it's going to subtract another 9.8. And a little bit more time thereafter, the velocity will reach zero. But once that velocity reaches zero, then it can't go any higher, and that's its max height. If it wasn't its max height, if it still had a positive velocity, then clearly a positive velocity means it's moving up and it would go higher. Or if you found that that wasn't the max height because the velocity was going downward, if the velocity was already pointing downward, then it clearly sped up to that velocity from some higher height. So in general, what that means is the velocity at the peak is in the y direction is equal to zero. So for part A, we say v sub y is equal to zero, and v0 sub y is equal to 30.00 meters per second, which we already had that v0 sub y. I just wanted to reiterate it there. So if I look for an equation that relates to time and relates quantities that we have, then I would want an equation that has v final, v initial, time, which we're looking for, and I also know acceleration, so that might come in handy. So all of this implies that we're going to get vy is equal to v0y plus a sub y times t. So with that in mind, I'm going to say 0.00 meters per second is equal to 30.00 meters per second plus negative 9.80 meters per second times t. And that gives me that t would equal negative 30.00 meters per second divided by negative 9.80 meters per second, like that. Now, when I divide 30 by 9.8, I get 3.061 seconds. So that's the actual time to Y max. So in other words, the time required to reach the max height is 3.061 seconds. And as I told you, it should be a little bit longer than 3 seconds because we know when we launch it at 30, it's going to lose 9.8 in 1 second. It's going to lose 19.6 in 2 seconds. And it's going to leave 27 or 28.4 in 3 seconds. So that's not quite 30. So it's got to go a little bit longer than 3 seconds. So this answer seems reasonable. Does that make sense to you? The 3.061? Okay. Now, part B, we want to know at what time will it reach its initial height. So in this case, we're actually trying to figure out how long it's going to take for it to go from 1 meter, reach its max height, and then come back to the 1 meter height. Well, to do that, I need to tie in the vertical position along with the vertical velocity. So the equation for that part, the equation for that part will be the y equals 1 half a sub y t squared plus v0 sub y t plus y0. And what I'm going to have is y final is equal to 1.00 meters. And of course, we already know y initial is 1.00 meters. And we also know what a is. So I can plug all this in, and I'm going to get 1.00 meters is equal to 1 half times negative 9.80 meters per second times t squared plus 30.00 meters per second times t plus 1.00 meters. You can see automatically that I can subtract 1.00 meters from both sides, and that's going to leave a 0 on the left and a 0 on the right. And specifically, what we now have is 0 is equal to negative 4.90 meters per second times t squared plus 30.00 meters per second times t. Now, we know that that is an equation set equal to zero, and we can factor out a common factor of t. So we can get, in fact, t, or let's say it this way. I'll go ahead and say from this, we can get 0 is equal to t times negative 4.90 meters per second squared times t plus 30.00 meters per second, close parentheses. So you see t is equal to, in one case, remember when you have a product is equal to zero, the only way the product can be equal to zero is if one of the factors is zero or the other factor is zero. So if I consider one factor being zero, I get t equals 0 seconds, but that's when we first took off, so that one's not relevant. And then the other solution is negative 4.90 meters per second times t plus 30.00 meters per second is equal to zero. In that case, I get t is equal to 30.00 meters per second divided by 4.90 meters per second, and therefore we get t is equal to 6.22 or 6.122 seconds. So 30 divided by, let's first off, yeah, 30 divided by 4.9 gives me 6.122 seconds. So this is t up to what I called it before is t at y0. So we found that the actual time at which this projectile, which we threw straight up, it's not really a projectile at this point, it's all one dimensional, but the time at which it reached its max height was 3.061 seconds, and the time that it reached its initial height was essentially double that, which would be 6.122 seconds. Now, for part C, we're asked specifically to find the velocity at which that it has when it reaches that initial height. So now that we know the time, we can actually use that with that other equation that we use for the velocity to find what the velocity is at that particular time. Now, that's requiring us to use an equation that we know, and that's fine, but it's also requiring us to use a result that we just calculated. Best case scenario is when you're solving a problem, especially for a test, it's best that you not use the results that you worked out during the test. If you have any way of doing it without using that result, then you're less likely to make a doubled up error. So if you happen to make a mistake on calculating the 6.122 seconds, if I now use the 6.122 seconds, then I'll have two problems that are wrong instead of just one. And a good instructor may not be paying close enough attention to realize that you did the second part right, even though you got it wrong. So it's best to sort of watch out for that. That being said, I'm going to go ahead and do it anyways because sometimes you just have to. So for part C, they want to know the velocity at t at y0 is equal to question mark. So I'm going to use v sub y is equal to v0 sub y plus at with a y there. That's pretty straightforward. We can just say vy is equal to 30.00 meters per second plus the acceleration is negative 9.80 meters per second every second times, of course, t. And that t actually, excuse me, I don't need to write the letter t here. That t is the 6.122 seconds. So when I do this math, I get 30 minus 9.8 times 6.122, and that gives me negative 30.00 meters per second is equal to the velocity at the time at which the height is y0. So that answers the sort of question why it's not smart to shoot a gun straight up in the air. Obviously, if you shoot it straight up in the air, even if it's a grown-ups moment where you're doing with a bow and arrow, okay, and actually a bow and arrow is probably a little bit more problematic. Because it's a little less air resistant, but there is some air resistance, so there will be some protection. But in general, if you fired a gun up from a height of 1 meter and it left with a muzzle velocity of, let's say, 400 meters per second, then if it wasn't for air resistance, when it got back to the height at which it was fired from, it would still be moving 400 meters per second again. But this time in the downward direction. That's why the negative showed up on here. So, in principle, a bullet could be going just as fast when it reaches its initial height as it left the gun with. And of course, if that hits you or someone else, that could be problematic. Now, the good news is it's actually going to be a little bit slower because air resistance. But if I told you to put on a bulletproof vest made out of a life preserver that's just blown up rubber, that's about the essential usefulness of that air resistance. So you're not going to get very much protection from your inflatable flak jacket, if you will. So now we have what the answer for part C was. I'm going to go ahead and write the letters by here. This was part A, this was part B, and this was part C. So we now know exactly how fast it was going. And in fact, because we're solving for velocity and we're not using that v squared equals v0 squared plus 2a y minus y0, that equation, I told people when I derived it, a lot of physics instructors won't allow their students to use it. And the reason why is because it's not a vector equation. And when it's not a vector equation, that means sometimes when you solve that equation for a velocity, you're going to have to choose the direction of the velocity, the sign of it. And that requires you to have some physical intuition. Using the v equals v0 plus at, I don't have to make such a decision, and it gives me a vector response. My initial velocity was positive 30 meters per second, which means in the one-dimensional context that it's going upward. And then when I find that the final velocity is negative 30.00 meters per second, that means it's going in the downward direction. So not only does it tell me how fast it's going, it also gave me the direction. Any questions on that part? All right. So we now got part C. Part D is where we wanted to know. Oh, no, I just did part D. I might have skipped part C. What was C? So A was if it's thrown from a height of 1 meter, what will be the max height? Uh, oh, that's the part I didn't solve. Okay, so what I did solve for was evidently part B and then part C and then part D. So let's change these letters real quick. I apologize for that, but this was part B because I'm just a goober that didn't notice it. So this is part B. This is part C, again, because I'm a goober and didn't notice it. So this is part C. And similarly, this and this is part D. So this one's going to be part D. That means I still haven't done part A, so I'm getting ready to do part A. I apologize for that. Part A was if it is thrown from a height of 1.00 meters, what will be the max height? So let me go back and draw part A real quick. Part A, we're going to use the equation y is equal to 1 half a sub y t squared plus v0 sub yt plus y0. And since I'm using the y0, it's actually going to give me the full height from ground level. By me saying y0 is 1 meter, I set the origin of coordinates at the ground. If I had said the initial height was 0, then I would have set the origin of coordinates at the height at which it left my hand. So by doing it this way, I actually get the max height, not just the maximum height it went relative to my hand. So I can plug in these numbers. It's going to be 1 half times negative 9.80 meters per second times, in this case, we figured out that the time required for it to reach the max height was the 3.061. So I can take the 3.061 seconds and square that plus 30.00 meters per second is the initial velocity in the y direction. And that's 3.061 seconds. And then plus 1.00 meters. So all of this should actually give me the answer, which I can fit down here, but just barely. So I'm going to take zero point 0.5 times negative 9.8 times 3.061 squared. Now I'm going to say plus 30 times 3.061, and then I'm going to say plus 1, and that's going to give me 46.92 is Y max. So that really was part A. Now, I didn't intend to do part A that way because I gave you part A first because I wanted us to do it without necessarily knowing what the time was. So that was a little bit more problematic. But since I put it as doing it after I'd already did part B, I could use that time. So let me show you a way that we could have done it only without having to solve for time first. So I'm going to call this A alternative way. So we do have the equation for y, but that requires time. But what we could also use is we could use v squared is equal to v0 squared plus 2. And since I'm doing this in the y direction, I'll go ahead and subscript these with y's. And this will be 2a times y minus y0, like that. So what we're trying to solve for really is y, the total y. Okay. So now I can put all these quantities in. We just have to make the argument that when I throw a ball up, it'll reach its max height, just like I did in part B, when the vertical velocity is 0. So I'm going to say, and I'll leave the units off this time because I think you've seen enough with the units. Uh, but it is good to at least put them down for the first step. So I'm going to say 0 squared is equal to 30.00 squared plus 2 times negative 9.80 times y minus 1.00. Okay, so with this in mind, I can go ahead and pull the 2 times negative 9.8 times y minus 100. I can pull that over to the other side, and that's going to give me 19.60, which is an extra digit, times y minus 1.00 is equal to 30 squared. And 30 squared, of course, is 900.0 with one extra sig fig there. Now I can divide both sides by 19.6. So I'll say 900 divided by 19.6 gives me 45.92. So now I'm going to get y minus 1.00 is equal to 900 divided by 19.60. And that's going to give me 45.92. And then therefore we can solve for y, and y is going to be 46.92 meters. So that's an alternative way of doing part A. And notice it's the same number that we got from the previous method, 46.92, 46.92. Any questions on that part? Okay, so that's just a way of solving a projectile, or in this case, a kinematics problem where you just threw a ball up. It was acting against gravity. This is what we call a object in free fall. The instant it leaves your hand, it's in free fall. And the big physics principle to understand here is that at the instant it leaves your hand, if you're ignoring air resistance, the acceleration during the entire travel will be negative 9.8 meters per second every second in the y direction, the downward y direction. Okay. It doesn't change. It's not negative 9.8, negative 9.8, negative 9.8. And then when it comes to a stop, the acceleration is 0. No, it's still negative 9.80. And then After it starts to fall down, the acceleration is still negative 9.8. The acceleration is still negative 9.8. When it just before it hits the ground, it's still accelerating at negative 9.8 meters per second every second. Okay. We'll learn in chapter 4 about Newton's second law, and what we see is that if the net force acting on an object is equal to basically mass times acceleration, so that unless the force changes, then the acceleration can't change. In this case, the force is just the force due to gravity, so it's not going to change. All right, now that we have done parts A through D, we have to do part E now. And part E says, what will be its speed when it hits the ground? Okay, so for part E, V for y equals 0 is the question mark. Okay, now what we have to do is, well, there's a couple ways we could do it. One could figure out how long it takes for it actually to hit the ground, and we already figured out how long it took for it to reach the initial height was 6.122 seconds, but we didn't figure out how long it would take to reach the ground. So we can do that now as well. We can say y is equal to 1 half a sub y t squared plus v0 sub y t plus y0, and we're going to set y equal to 0, and this will give us a way to solve for the total time that it's in the air. Specifically, this is solving for the hang time. There's other ways you could do it, but this is the way I'm choosing to do it in this particular instance. So I'm going to say 0 meters is equal to 1 half times negative 9.80 meters per second times t squared plus 30.00 meters per second times t plus 1.00 meters. That's the whole equation, and you can see it's a quadratic equation. Okay. The reason why I'm doing it this way is specifically so you'll understand, hey, I need to know the quadratic formula. Hopefully you already have it memorized. If you don't, that's okay. It's also valuable, or it's also included in the values that are in the table that we get with the test. So what this becomes is negative 4.90, I'm dropping the units now, times t squared plus 30.00t plus 1.00 is equal to 0. And the formula is when ax squared plus bx plus c is equal to 0, then x is equal to negative b plus or minus the square root of b squared minus 4 times a times c, all that over 2a. So in this case, t is going to be equal to negative b, which would be negative 30.00. Remember, that's, of course, has units of meters per second, plus or minus the square root of b squared, which would be 900.0. Of course, that's b squared, and b was the coefficient of the t, which is the velocity. So this would actually have units of meters squared per second squared, minus 4 times a, which would be negative 4.90, and that's meters per second, and then times c, and that's 1.00, that's meters. So notice the negative 4.90 being in meters per second, and then multiplied by the meter gives me meters squared per second squared, all under the square root. So that's good. It looks like it's dimensionally consistent. Not only that, because the a term was negative, there's no way you can get a negative under the square root. So we're going to get a good positive value. And then 2a would be negative 9.80. And of course, that's in units of meters per second per second. So we're going to have meters per second divided by meters per second. And that means it should come out to be just seconds. Let me work out this. This is negative 30.00 plus or minus 900 plus 4 times 4.90 times 1 is giving me 919.6. And then all this would be over negative 9.80. 9.80. And I've already worked out the details of the units, at least verbally, for you guys. The square root of 919.6 is 30.32. So I'm going to say negative 30.00 plus or minus 30.32 divided by negative 9.80. Now, what you see here is if I do the minus sign, I've got a plus or minus here. The top one's plus and the bottom one's minus. If I do negative 30 minus negative 30.32, I get a really big negative number, but then I divide it by a negative number, and that gives me a positive number. If I did negative 30 plus 30.32, I'm going to get a really small positive number. And then when I divide that by a negative number, it's going to become negative. So it's clear that only the bottom sign is one that makes a physically realistic answer. So only the bottom sign makes sense. I almost wrote SINCE, which is not the right version of sense, but that's how awesome my brain is nowadays. So I'm going to say uh, negative 30 minus 30 point, excuse me, negative 30 minus 30.32. And now I'm going to divide that by negative 9.80. And that's going to give me 6.155 seconds. So T hang time is slightly bigger as we expected. It's slightly bigger than the time required for it to reach its initial height. Remember, that was 6.122 seconds. In this case, we got 6.155 seconds. Technically, with the sig figs, 3.30 minus 30.32. Oh, that gives me 4 sig figs divided by 3. So I really should only have 3 sig figs. So I'll circle it that way. That's not the answer we've been asked for because we were asked for in part E. We wanted to know what will be its speed when it hits the ground. So we want to know the speed at that time. Now I can use that time and the other equation, v equals v0 plus at, to figure out the velocity. So with that in mind, I can say v y is equal to v0y plus a sub yt, which is going to be 30.00, again, leaving the units off because I've done enough with that, plus negative 9.80 times 6.155, like that. And that gives me v sub y is equal to 30 minus 9.8 times 6.155. And that gives me negative 30.32 meters per second with one extra digit that's not a sig fig. So the final velocity just the second before it hits the ground is negative 30.32 meters per second. Notice that happened to be what came out of the square root, but that's sort of the nature of the way that equation was made up. So we now have the velocity that the projectile or that the ball had just the instant before it hit the ground. Okay, we're calling it's literally the time at which it hits the ground, but the main thing is if the ground wasn't there, it would keep accelerating. So you're just going to calculate that as if it didn't come to a stop. For some reason, students tend to fixate on that and they'll say, oh, the velocity when it hit the ground was zero. Well, it's only going to be zero for a split second because it's more than likely going to bounce a little bit. So really, it's just the velocity that it has at that time is sufficient. Now, that was part E, and then part F said, how long will it take to hit the ground? That was the T hang time that I told you about, so I've already worked that. So part F is T hang time is equal to 6.155 seconds. So now I also have part F solved. Any questions on that?
No,
Now, let's try. Go ahead. You getting ready to say something, Michael?
no, I was just saying no. Sorry.
Okay, cool. Let's try another really simple problem here. With this problem, let's say consider a ball rolling along a flat, frictionless surface. Okay. A, excuse me, I forgot to say what the velocity at which it wishes to be rolling along a flat, frictionless surface is. So consider a ball rolling along a flat, frictionless surface at 40.00 meters per second. Part A, how fast will it be going at t equal 3.061 seconds? Part B, how far will it have rolled at that time? Okay. C, how fast will it be going at t equals 6.122 seconds? D, how far will it have traveled at t equals 6.122 seconds? And E, how fast will it be going at t equals 6.155 seconds? And F, how far will it have traveled at t equals 6.155 seconds? Okay, so that seems a little odd, but the key thing to understand here is if the actual ball is rolling on a horizontal surface, it's not going to be sped up or slowed down because the net force on it is zero. The friction force is zero, and if it was tilted, if the surface that it was on was tilted, there would be an acceleration. You don't necessarily know how to calculate that acceleration right now, but you know that if it's perfectly level, it shouldn't have any acceleration associated with it. So this object has no acceleration. So when you take an equation like y equals 1/2 at squared plus v0t plus y0, the a term is zero, so you get just y is equal to y0 plus v0 times t. And an equation like v0 or v equals v0 plus at, if the acceleration is equal to zero, that means v is equal to v0. So y equals 1/2, or let's do this since it's horizontal. I'm going to go ahead and use it in the x variables. So x is equal to 1/2 a sub x t squared plus v0 sub x times t plus x0. If a is equal to zero, this becomes x is just x0 plus v0 x times t. Similarly, V equals V0 plus AT, if A is equal to 0, becomes V is just equal to V0. Okay? So, with that in mind, I say part A, how fast will it be going at t equals 3.061 seconds? At t equals 3.061 seconds, V equals 40.00 meters per second. That's the answer. Oops, I meant to write that in a different color. Part B, it says how far will it have rolled at that time? Well, that means x is equal to 0 plus 40.00 meters per second times 3.061 seconds gives me 40 times 3.061 equals 122.4 meters, and that's the answer to part B. Part C says, how fast will it be going at 6.122 seconds? At t equals 6.122 seconds, v is equal to 40.00 meters per second because, as we said, the acceleration is 0. Now we do part D. How far will it have traveled at 6.122 seconds? So again, x is equal to 0. Notice x is equal to 0 plus because I'm assuming that I released the ball rolling at 40 meters per second from the origin so that x0 is actually equal to 0. So that's why I'm using the 0 out there. But in this case, it's just going to be 40.00 meters per second times 6.122 seconds, like that. And that's going to be 40 times 6.122 gives me 244.9 meters. And that's only good to 3 sig figs roughly. So I'm going to underline it like I did there. So that's part D. Now I'm going to do part E. Part E says, how fast will it be traveling at 6.155 seconds? At t equals 6.155 seconds, v is equal to 40.00 meters per second because the acceleration is 0 again. And finally, part F, how far will it have traveled at that time? Well, x is going to be equal to, I'll leave the units off this time, 40.00 times 6.155. So 40 times 6.155 gives me 2.4 or 246.2. And that's it. Okay. Now, this problem might seem really weird, but the whole purpose of me doing this is so you'll understand how to solve projectile motion problems. So I've done two examples now. Let's call this example 2. Let's call this example 1. Okay. Now I'm going to solve a projectile motion problem. Let's say, consider a projectile fired from a height of, that H turned out really badly, so from a height of 1.00 meters with a velocity of 50.00 meters per second at 36.87 degrees above horizontal. Okay. Part A, at what time will it reach its max height? B, what will be its velocity when it reaches that max height? C, how far horizontally will the projectile be from its initial position when it reaches that max height? And D, what is that max height? E, what is the projectile's time aloft, which means the same thing as hang time. So, what will be the projectile's time aloft means how long is its hang time? And F, what is the distance horizontally from the initial position to where it hits the ground? Okay. And G, what is its velocity just before it hits the ground? Okay. So that's a typical projectile motion problem. What we're given here is a figure. I'm going to go ahead and draw a coordinate system to make it make a little bit of sense. So this is our x-axis. This is our y-axis. This is 1.00 meters. The object is actually going to be fired at 50.00 meters per second at 36.87 degrees above horizontal. And it's going to take off like this and land over here, which I've just run out of space. So let me extend my coordinate system a little bit further. Oh, let me use the right color. And now let me fix that projectile motion, which got a little shaky there. So it's going to reach some max. Oop, there it is again, blue. Going to reach some max. Dang it. I keep changing it to blue, but it keeps going back to black. Okay, so the distance that it traveled horizontally is called the range. So I'll write range right here. The max height is y max. The time at which that occurs is t y max. And of course, it's going to have a specific velocity v at y max right there as well. And we're going to also have a t aloft, which is t hang time. And of course, it's also going to have a final velocity, which we're looking for, and that will have some angle phi that it makes with the horizontal. Okay. So to solve a projectile motion problem, I've told you that it's two problems simultaneously. There's a ball that's been thrown straight up vertically, and then there's a ball that's traveling horizontally with no acceleration whatsoever. And those two are linked just because they're doing the thing that the shadow does. In the case of the ball, that's doing what the shadow does as it moves along the ground. And the vertical ball is doing what the height of the ball does as motion is going along. So the first thing we have to do is break the initial velocity up into x and y components so we can figure out what the vertical component of velocity is and figure out what the horizontal component of velocity is and go from there. So using that idea, I'm going to take this as 50.00 meters per second, and this is 36.87 degrees. We can see, in fact, that the horizontal component of velocity obviously points to the right, and the vertical component of velocity obviously points up. So this is v0 sub x, and this is v0 sub y. And while you're first starting out for chapters 2 and 3, for instance, is probably a good time to go ahead and just write sine and cosine every time you deal with a vector. Just write them out, figure out what they are, and then let yourself decide which one I need for the y component, which one I need for the x component. Because a lot of times people will teach this as if cosine always gives you the x and sine always gives you the y. That is not the case if you are free to use any angle you want. So it's always best to just sort of play it out and figure out what sine and cosine are in each case. So what I'm going to say is the sine of 36.87 degrees is equal to opposite over hypotenuse. And of course, the right angle is right here. So that tells us the hypotenuse is 50. And the side that's not touching the angle is the opposite. So that's V0y over 50.00 meters per second. So that tells us V0y is equal to 50.00 meters per second times the sine of 36.87. And the sine of 36.87 is actually 3/5. Now, if you put it in your calculator, it's going to come out really, really close to 3/5. And I don't need you to memorize this. It's just something that I know. But you can tell that this should be 30.00 meters per second. Check it with your calculator just to see. It might be 29.999 or something, or it might be 30.001. But the main thing is you got that. Now I'm going to do the cosine of 36.87 degrees is equal to adjacent over hypotenuse. Remember, the adjacent side is touching the angle, and then the hypotenuse is pointed to by the right angle. So the adjacent side is V0x, and of course, the hypotenuse is 50.00 meters per second. So that says V0x is equal to 50.00 meters per second times the cosine of 36.87. But the cosine of 36.87 is, in fact, 4/5. So in this case, you get 40.00 meters per second, like that. Notice the velocities. When I did example 2, the ball was rolling horizontally and had a velocity of 40 meters per second. That's the same thing as the x component. When I did example 1, I threw the ball upward at 30 meters per second, right? And what we just found is the vertical component of velocity is 30 meters per second. So I've already worked out the details, in other words. So now we start with, at what time will it reach its max height? Well, we know that occurs when the y component of velocity is equal to 0. So we can go ahead and say, and I think I wrote this in green, didn't I? Yeah, I did. So I can say Vy is equal to 0 at max height. Therefore, Vy is equal to V0y plus AT implies 0 is equal to 30.00 meters per second plus negative 9.80. I'll leave off the units here just because it's getting ugly, and then times t. So in this case, I get t is equal to 30.00 divided by 9.80, and that gives me 3.061 seconds. And we knew that because that was the answer we found in part A, or in example 1. Okay? So at what time will it reach its max height? That's 3.061. It's at max height. Now for part B, it says what will be its velocity when it reaches the max height? Well, in this case, we've got an x component of velocity and a y component of velocity, right? At every point in the projectile motion, we have an x component of velocity and a y component of velocity, like this. But at the max height, the y component is 0. So when we go to figure out what the velocity is, we want to know velocity at y equals y max. Well, Vy is equal to 0 at max height. But Vx is equal to 40.00 meters per second. And we know that because in example 2, we found at 3.061 seconds, how fast will it be going? 40 meters per second, right? So we can go ahead and say that the velocity at y max is equal to 40.00 meters per second, and it's purely horizontal. So the easiest way we can write that is just write an I hat next to it, because that's what we learned we can do when we're wanting something to point in the y direction. That last part worked out kind of badly because I drew over the vector symbol. So there's the velocity at max height. Does that make sense? Now we can go on to part C. And part C says, how far horizontally will the projectile be from its initial position when it reaches that max height? Well, we know that the shadow along the ground is moving at 40 meters per second to the right. So if I just knew how far that shadow could move, if it moved 40 meters per second for 3.061 seconds, I would have exactly the right answer. If I look at example two, though, what I will see is that how far will it have rolled at that time? The answer was 122.4 meters. So that's actually going to be the answer. So x at y max is given as follows. X is equal to x0 plus v0x times t, and x0 of course is equal to 0, so I just get 40.00 meters per second times 3.061 seconds, which equals 122.4 meters. Of course, you can obviously go ahead and uh, calculate that yourself, but we really didn't need to, so that's why I just used that number. So 122.4 meters will be how far it is horizontally from the place where it was fired. So if I go back on the diagram, what that means is this distance is 122.4 meters from here to here. Now for part D, we say, what is the max height? Well, I would like to know the max height, and what we figured out is that it reaches the max height at 3.061 seconds. So I could use that time and calculate the max height by using the y equation, and that would use a result that we already calculated. So that wouldn't be the most ideal thing. So the better way would be the alternative method, and that's what I'm going to do. I'm going to say for part D, we want to know y max equals question mark. What we know is vy squared is equal to v0y squared plus 2a sub y times y minus y0. What we want to know is y max, so I can put all this in, and I'm going to say 30.0. Actually, the velocity in the y direction at max height is 0. So this is going to be 0 meters per second squared is equal to 30.00 squared. I'll leave the units off for the rest of the part. Plus 2 times negative 9.80 times y minus 1.00. So again, we're going to end up solving for y. We'll get 19.60 times y minus 1.00 is equal to 900.0. Therefore, y minus 1.00 is equal to 900.0 divided by 19.60, and 900 divided by 19.6 gives me 45.92. So the y max is equal to 46.92 meters, because we have to add 1 to both sides to actually solve for y. So plus 1.00 plus 1.00. That's how I got 46.92. Does that make sense? All right. So that was the way we did it, and I didn't have to use any variables that I'd already calculated, so that's a little safer. Now we'll go to part E, and part E says, what's the projectile's time aloft? So for part E, what we're going to do is say T hang time is equal to question mark. Now, what we know is y is equal to 1 half a sub y t squared plus v0 y t plus y0. And we know that that really dictates everything because the vertical motion tells you how long it has aloft because we know it's going to lose 9.8 meters per second vertically every second. So that vertical component of velocity, which is 30 meters per second, it's going to have to be a little longer than 6.122 seconds because 6.122 seconds was the time it took to go from 1 meter back to 1 meter. And in fact, what we found was the time required for it to go from 1 meter back to 0 meters was 6.155 seconds. That's what we're shooting for. And what we're going to do is solve it using that same equation. So now I can plug all this in. I'm going to say 0 is equal to negative 4.90. Notice I'm leaving the units off. Times t squared plus 30.00 times t plus 1.00. And that gives me t is equal to negative 30.00 meters per second plus or minus the square root of 900.0 meters squared per second squared minus 4 times a, which is negative 4.90. I should go ahead and say that's meters per second times 1.00 meters, and then all of this would be divided by negative 9.80 meters per second. Now, we know exactly what this is going to be. This time turns out to be 6.155 seconds. So that's equal to our hang time, which is also t aloft. And that's our answer for this part. Does that make sense? Okay, now F, what is the distance horizontally from the initial position to where it hits the ground? I'm asking for the range. So that's pretty straightforward. We know exactly what to do. We know how long it's aloft, and all that time, that ball is rolling horizontally at 40 meters per second for that whole 6.155 seconds. So that ball is going to have rolled 6.155 seconds times 40.00 meters per second, and that allows us to calculate the range. So what we know is x is equal to x0 plus v0x times t. But you can see from the original diagram, the initial x position was x equals 0. So that's why I said x0 is 0. All I have to do now is plug in 0 plus 40.00 meters per second times 6.155 seconds, and that's going to give us our 244.9, I think it was. No, that's going to give us a 246.2. The point 0.9 was the distance it traveled to reach 1 meter. So 240, oops, where'd I go? 246.2. So we're going to say equals 246.2 meters. So R equals range equals 246.2 meters. Obviously, I'm throwing caution to the wind with regards to sig figs. I was sort of keeping track of it for a little while, but I really don't care too much about sig figs other than teaching you how to deal with them. I think I've done enough to teach that. So I'm just giving you the answers full out and going with it. So we now figured out the range is 246.2. So just to show you what that means on this diagram, 246.2 meters is that distance right there. Again, we didn't know that when I drew the diagram. I'm just putting it on there now so you get an understanding of what it was. We did find the hang time was 6.155 seconds. We did find that this was 3.061 seconds. We did find that this was equal to 40.00 meters per second in the I hat direction. And I'll put a little vector symbol there. We also found that the max height, did I actually solve for that one? What is the max height, part D? Yeah, 46.92. So now I've sort of filled out all that stuff except for the final velocity, which we'll do in a second. So I've gotten part F, which is the range. And then all we have left is what is its velocity just before it hits the ground. Oops. V final equals question mark. Uh, can you tell me what the horizontal component of velocity would be when it hits the ground?
The horizontal component, as in, are we using the range?
Uh, just because remember we're separating the motion. There's a vertical motion where it speeds up or where it slows down, slows down, slows down, comes to a stop, and then speeds up, speeds up, speeds up, down, and then hits the ground. But
So
horizontally, go
it'd
ahead.
be zero.
Yeah, well, close. You're thinking the right way, but you just got mixed up on your numbers.
Okay.
Because the acceleration in the horizontal direction is zero, the velocity is always 40 meters per second. That's why we did this part right here, A, C, and E. We found the velocity was 40 meters per second horizontally. So using that, I can say V final X is equal to 40.00 meters per second. And that's what we were figuring out when we did example two. Now, to find out what the velocity in the y direction is, we're going to have to use one of our equations. Vy is equal to v0y plus a sub yt. We can use that and that'll be fine. We could also use the v squared equals v0 squared plus 2ax, and that would allow us to do it without knowing anything about the time. But I'm going to go ahead and use it with the time. So what I had was the initial velocity was 30 meters per second upward minus 9.80 times the time, which is 6.155 seconds. And this should give us our final component of velocity. And if you remember correctly, that turned out to be negative 30.32 meters per second. I'm going to double check my math. Yeah, negative 30.32 meters per second. But you can get that from just doing the math that I just showed you. So that's our y component of velocities downward. Now, to make it a vector, because I asked for velocity, velocity is a vector quantity. So I actually have to recompose the vector out of the component. So I'm going to turn to the next page and say G continued. What we have here is our axes like this. And what I have is a y component of velocity that is actually in the negative direction and is negative 30.32 meters per second. But then I have a x component of velocity, which is a bit bigger, and that's positive 40.00 meters per second. That means the final velocity, v final, is given by this, and I'm going to call this angle. Let me go ahead and redraw this a little bit. I'm going to get rid of that, and I'm going to take this black pen and draw it a little further along, and I'm going to say that this angle right here is phi, and I think you can realize that if that angle's phi, notice the green line here is parallel to the black line here, and then this line right here is a bisector. So this angle and this angle are alternative internal angles. If you haven't had geometry, you might not know any of that terminology. So I'm teaching it to you now. But basically, if you have railroad tracks, they have to be parallel. So if you have two tracks for a railroad track, if you lay a piece of rebar diagonally across it, then alternate interior angles are equal. And what I mean by alternate is they're on opposite sides of the rebar. So you can see this is on one side of the rebar, that's on the other side of the rebar, but it's an alternate interior angle, and interior means it has to be between the parallel railroad tracks. So that angle VF is the same as this angle right there. Okay, so I'm calling it phi. So now I can go ahead and compute that V final is equal to the square root of 30.32 meters per second. Now, technically that's negative, but we're going to square it so it don't matter. Plus 40.00 meters per second squared there as well. So the magnitude of this becomes 30.32 squared, and that gives me 919.3. And then 40 squared, that gives me 1,600. If I add the 1,600 and the 919.3, I get the square root of 2,519. Yes. Meters squared per second squared. Now, if I take the square root of that, I get 50.19 meters per second is the magnitude. Now, I can also say that tangent of phi is equal to opposite over adjacent. So that would be 30.32. Notice I'm not putting the sign in there. Divided by adjacent, which would be 40.00. So phi is equal to the inverse tangent of 30.32 over 40.00, which equals shift tangent inward inverse 30.32 divided by 40, close parentheses. That gives me 37.16 degrees. So the final velocity would be V is equal to 50.19 meters per second at 37.16 degrees below horizontal. So that's it. That's the big trick. That's all that's required for solving projectile motion problems. You've sort of got two problems going on at once, and you just use the time to relate them. The time is always dictated by the vertical component. Once you break the velocities up into horizontal and vertical components, the vertical component is the one that allows you to figure out the times. So the time, for instance, for it to hit the ground, the time for it to reach its max height, the time for it to reach the initial height, all that stuff comes from the equations related to the vertical motion. And anything that wants to tell us the horizontal component of velocity, that's never going to change. It's always that same horizontal component of velocity. And if you need to go know anything about how far it's going to the right, you're just going to use that horizontal component of velocity and the time you got from the y component of velocity equations. Does that make sense? All right. So that is a bona fide solved projectile motion problem. Hopefully, that's a good starter on helping you understand exactly how it's done. Now, I'm going to do it symbolically because I need to teach you. If you look in your book, for instance, it says in chapter 3, we cover vectors and scalars, addition of vectors, graphical methods, subtraction of vectors, and multiplication of a vector by a scalar, adding vectors by components, unit vectors, vector kinematics, projectile motion, solving problems involving projectile motion, and then relative velocity. What it starts to talk about, though, in this projectile motion is really what happens from a vector standpoint to these velocities and derivatives and that sort of stuff. So I'm going to show you in a more general sense exactly what's going on vectorially so that you can, even though I'm not going to require it, you can do all this with vectors. So let's go on and consider a projectile motion problem. So again, I'm going to start off with a coordinate system. I keep hitting this iPad while I'm trying to draw, and it makes everything go crazy. So what we're going to assume is that we have initial velocity v0, and that's at an angle theta. Now, that's going to cause a trajectory that actually turns out to be a parabola. And in order to show that it's a parabola, we would need to write an expression for y versus x, not y versus t and not x versus t. So that's something you can do. But I'm going to call this value right here the range. But we're also going to realize that there is a final velocity vf and that there's an angle phi that final velocity makes. We're also going to realize that this is y max and this is t hang time. Actually, I won't put a question mark on it. I'm just going to write it down there and show that it's t hang time. And those are the relevant parameters. We want to find how far afield it lands, in other words, the range. We want to know how long it's in the air. We want to know what its final velocity is, and we want to know its hang time. So we can use a very specific vector, and this vector is called the position vector, and it's r. We use the symbol r because that's neither x nor y nor z, and the motion could involve x and y and z, so it wouldn't be reasonable to call it x or y or z. So we say the position vector is r. So we'd say r of t equals the position vector. V of t is equal to the velocity, and a of t is equal to the acceleration. Now, we already learned something. We specifically learned that v of t is dr over dt. Remember, we learned it in the context of one dimension where it's dx dt. But in principle, it's going to be dx dt is the x component and dy dt is the y component. So that's how I'm fixing that. And additionally, a is going to be dv dt, which is d2r over dt squared. Okay. Now, let me show you what the position vector is in the most general sense. So in the most general sense, r of t is equal to 1/2 a sub x t squared plus v0 sub x t plus x0, all of that times I hat. Notice what all I did was I took the most complete position kinematic equation, which is x equals 1/2 at squared plus v0t plus x0. That's all I did. Now I'm going to do the same thing for the y equation. and that's going to be 1 half a sub y t squared plus v0 sub yt plus y0, and that's going to be in the j hat direction. Now, we could also write this a little easier with 1 half a sub x t squared plus v0 xt plus x0, comma, 1 half a sub y t squared plus v0 sub yt plus y0, and then greater than symbol. That's another way of writing it, so we could avoid writing I hat and j hat. We could also replace the I hat with x hat. We could also replace the j hat with y hat. That would be acceptable as well. But for projectile motion, for simple projectile motion problems, A of t is just equal to negative g j hat. In other words, there's no acceleration in the x direction. And the way I've got it drawn in this diagram, x0 is equal to 0 and y0 is equal to 0. So I can now say r of t is actually equal to v0x times t I hat plus negative, or I should say minus. No, I'll do it this way. I don't want to write that minus out in front. That could cause some problems. I'm going to use parentheses. Maybe I'll even use square brackets. So this is going to be negative 1 half g t squared plus v0 yt times j hat. So that's our position as a function of time for the diagram I have drawn. If I was actually having it land at a different height or take off at a different height other than 0, then I might have an x0 and stuff like that in it, and I might have to do more stuff. But in this one, I'm just launching it and it's landing at exactly the same height. So it makes it a little bit easier, but we'll just go from here. Now, we have the diagram that shows the initial velocity is v0 and it's at an angle theta. And that, of course, has a x component and a y component. So v0y is just v0 times the sine of theta, and v0x is just v0 times the cosine of theta. Remember, cosine often gives you the x and sine often gives you the y, but not all the time. So with that in mind, I can now say r of t is equal to v0 t cosine theta I hat plus negative 1 half gt squared plus v0t sine theta j hat. That's it. That's the velocity as a function of time, given all the initial conditions we were given. From that, we can take v of t is dr dt. And the beautiful thing about using I hat and j hat and k hat is they're actually constant unit vectors. So when you take the derivative, you can either pull those out in front and then just take the derivative of everything else, or you can just take the derivative of everything else and just put the I hat after it. They don't partake of the uh, integration or the differentiation. They're always just a constant. However, if you switch to other coordinate systems, as we'll do in 242, then you have a theta hat and an r hat and a phi hat. Those things are actually functions, and you would actually have to take the derivatives of those, but you don't have to here. Now, the derivative of v0t cosine theta with respect to t is just equal to v0 cosine theta I hat. The derivative of negative 1/2 gt squared plus v0t sine theta with respect to t is going to be equal to g negative gt plus v0 sine theta. And that is in the j hat direction. So now I have the velocity as a vector function of time. This is what we call a vector valued function. It's a function that takes in this case, we're pretending like it takes in just one variable time. And it sort of does because I'm saying the initial angle and the initial velocity are actually constants. But now we have the velocity as a function of time. The acceleration as a function of time, of course, a of t is just dv over dt. So I'm going to take the derivative with respect to time of v0 cosine theta. Do you see any t's in that? The derivative of v0 cosine theta? There's no t in it, is there? So the derivative of that is 0. When I take the derivative of negative gt plus v0 sine theta, I just get negative g. And then that's multiplied by j hat. So from a vector valued function standpoint, that's the motion that we're actually doing here. Now I've got a vector valued function for position as a function of time. I've got a vector valued function for velocity as a function of time. And I've got a vector valued function for acceleration as a function of time. That's really all you need to do. Now let's go about solving for things like y max and so on and so forth. So what is the max height? Well, we know that y as a function of time has a maximum at y max. So that's one way we could do it. But we also know that the velocity in the y direction would be 0 at y max. So we could use either one of those. We could say that y versus x is a function of, or excuse me, y versus x has a maximum at y max. That would be something we could do, but we would need y as a function of x instead of y as a function of t. The way we'd make y as a function of x is we could solve for t and then replace the t variable with the x using things like x is equal to v0 sine theta times t. And then t would, of course, be x over v0 sine theta, something like that. But in this case, we're going to say y equals y max when vy is equal to 0. So y of t, well, let's say this. So r of t is equal to something plus, no, I don't want that. That's not helpful. I can take v of t. We found that was actually equal to v0 t, or actually v0 cosine theta I hat plus negative well, actually, when we took the derivative of that, that just became negative gt plus v0 sine theta j hat. So Vy equals 0 implies negative gt is equal, or excuse me, negative gt plus v0 sine theta is equal to 0. And that tells us that gt is equal to v0 sine theta, or specifically t is equal to v0 sine theta over g. Now that's actually t at y max. So I need to subscript it that way so we know what that t means. So t y max is equal to v0 sine theta over g. So now we know at what time the max height is reached. Now we just need to figure out what y is at that time. So now we try to determine y at t y max. Well, r of t is equal to v0t cosine theta I hat plus negative 1 half gt squared plus v0t sine theta, like that, j hat. We want the y part, so what we want is y max is equal to negative 1 half gt y max squared plus v0t y max sine theta. So what I'm going to do is take the negative g over 2 and I'm going to multiply it by the time we just found, which was v0 sine theta over g, and that's got to be squared, plus v0 times v0 sine theta over g times sine theta. So we get y max is equal to, notice we get negative v0 squared sine squared theta over 2g squared times the g we already had out in front. So that g is going to cancel out with this g up there, and that'll just give us v0 squared sine squared theta over 2g, but we still have the other term. The other term is plus v0 squared sine theta squared because there's a sine next to it, and that's over g. So we get negative v0 squared sine squared theta over 2g plus v0 squared sine squared theta over g. To get a common denominator, we need to multiply by 2 over 2, like that. And that's going to give us negative v0 squared sine squared theta plus 2v0 squared sine squared theta, all that over 2g, and v0 squared minus plus 2v0 squared is going to give obviously positive v0 squared. So we get y max is equal to v0 squared sine squared theta over 2g. And I'm using green to circle the results in this case. So that's our actual value for the max height. Again, this was going on the assumption that we launched it from ground level and it's ultimately landing at ground level. So the height is all measured from the same ground level. But that's our Y max. So we've already gotten that. We've also managed to find the time at which uh, the max height is reached. We can go on further and say, okay, well, what about the hang time? What is the hang time of the projectile? Well, in that case, y equals 0 at t equals t hang time, which I'm going to abbreviate THT like that. So we know that R of t is equal to V0t cosine theta I hat plus negative 1/2 GT squared plus V0t cosine. Oop, that one's supposed to be sine theta. Sine theta times J hat. So I want to set y equal to 0. That means 0 is equal to negative 1/2 GT squared. That's t hang time, by the way, plus V0t hang time sine theta. Oops, I left off a. No, I didn't leave off cosine. That's good there. And that's what I need. Now I can factor out a common term of t hang time, and that's going to give me 0 is equal to t hang time times v0 sine theta minus 1/2 gt. So this means either t hang time is equal to 0 or t hang time is equal to, in this case, we're going to basically say 2v0 sine theta over g. And that's actually the right answer. The t hang time equals 0 was the time that it left. So this one's the real one, but now we have the formula for T hang time. And notice that it's exactly twice T max. T max was V0 sine theta over G. In this case, T hang time is 2V0 sine theta over G, which is exactly what we expect. That previous problem we did was a little more complicated because the projectile was launched from 1 meter above the ground. So there was a little bit extra time between the time it reached that initial height and the time it reached the ground. In this case, it's perfectly symmetric, so we don't have to do that. Now that we know T hang time, we can say, what is the range? Well, range is equal to x at T hang time. So if I just take the x position, the equation that we have in the R, in other words, at T hang time, then that will give me the range. Well, I know that X for T hang time is going to be basically, if I look back at my R0, I see that right here, the X position is just V0T cosine theta. So all I need to do is plug in T hang time for that T right there. So R is going to be equal to V0 times 2V0 sine theta over G, and then that multiplied by cosine theta because the cosine theta was already there. Now, this is exactly right, but there's a simplification we can make. I'm going to make it this way. I'm going to say V0 squared times 2 sine theta cosine theta over G. That is the right formula. But if you look in some of the mathematical quantities that were given under useful references, we can see that there's an identity for 2 sine theta cosine theta. In fact, 2 sine theta cosine theta is actually equal to sine of 2 theta. So, with that in mind, we can now say that R, the range, is equal to V0. Oops, might need to pin here. It's equal to V0 squared sine 2 theta over G, and that's exactly the right answer. And not only that, the nature of the way sine theta works, the fact that it's sine of 2 theta tells you that other than when you're trying to get the absolute maximum range, which again, if you ignore air resistance, the maximum range occurs when theta is equal to 45 degrees. If you're not shooting for 45 degrees, then you have two choices for each range that you want. You have a low trajectory and a high trajectory. And you've probably seen this. Like if you see Shaquille O'Neal try back when he was an actual player, when you used to see him try to play basketball and shoot free throws, he was really tall and horrible at shooting free throws, mostly because he really used a low trajectory. If you use a high trajectory, it gives you a little bit more room for error in general to have it actually bounce in. Whereas the low trajectory, you can bounce it off the front of the rim, you can bounce it off the back of the rim, you can bounce it off the backboard. All of that's going to lead to crap. Whereas in a high trajectory, it goes up like this and it's coming back down. Chances are it could hit the back of the rim, in which case it'll bounce off, hit the backboard, and then fall back in, or it could hit the front of the rim, which could mean that it's too short and it's going to fall down, but it also could mean that it's a little too long and it bounces off the front of the rim into the back of the rim and then back into the basket as well, or from the front of the rim to the backboard and into the basket as well, or it could just skim across the front of the rim and go into the basket as well. So there's a lot more probability that it's going to go in that higher trajectory. And that's what this shows. Let me explain to you how that works. Remember, when we're shooting a projectile, it doesn't make any sense to have an angle that's higher than 90 degrees because once it reaches 90 degrees, you're throwing it straight up. That's not a projectile anymore. That's just an object being shot straight up. And if it goes past 90 degrees, then it's less than 90 degrees, but you're shooting it the other way. That's the key thing to understand here. So, with that in mind, I'm going to make a plot of the sine of theta versus the sine of 2 theta. So, this is theta on the horizontal axis and y equals the sine of 2 theta. Now, normally, y equals sine theta and theta goes like this. It's basically a peak and then a trough like that. This is the angle 2 pi. This is the angle pi. This is pi over 2. This is 3 pi over 2, so on and so forth. But when we have the angle of sine equals 2 theta, the sine of 2 theta, then basically that whole trajectory stretches out over a distance of just plain theta. So I'll put, or excuse me, of just plain pi. So I'll put pi right here, and then we'll see 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4 would be right about here. So in this case, we're going to say that's 3 up, that's 3 down. So oops, my sine graph is going to look like this. And remember, pi is equal to 180 degrees. Pi over 2 is equal to 90 degrees. So projectile motion only occurs between theta being greater than 0 degrees and less than 90 degrees. That's all projectile motion. In other words, the angle bigger than 90 degrees or bigger is not valuable, and an angle as small as 0 degrees is not valuable. The only ones that really matter are the angles between 0 and 90 degrees. So if you want to shoot for a particular value of sine of 2 theta, you can see that this is one of the thetas, theta 1, and this is the other theta, theta 2. And in fact, 90 degrees minus theta 1 is exactly equal to theta 2 minus 90 degrees. In other words, the difference between the angle and 90 degrees is the same for both trajectories. Or actually, I should say between 45, not 90. Sorry about that. But I don't even need the absolute value bars uh, because of the order that I put them in. But if you chose to just say the difference in them, then you'd have to use the absolute value bars. So what I'm going to say is 45 degrees minus theta 1 is equal to theta 2 minus 45 degrees. And of course, 45 degrees is also pi over 4. So pi over 4 minus theta 1 is equal to theta 2 minus pi over 4. So for instance, if I said theta 1 was equal to 22 degrees, what would theta 2 be? Well, 45 degrees minus 22 degrees is actually equal to 23 degrees. And then theta 2 minus 45 degrees has got to equal 23 degrees as well. So that means theta 2 is equal to 45 plus 23. That would be 68 degrees. So theta 2 is 68 degrees. So that's how you find your high and low trajectory. If you can shoot at a certain distance, you're fine. Now, if you happen to be trying to get sine of 2 theta equal to 1, then obviously that can only happen at pi over 4, which equals 45 degrees. So, uh, ignoring air resistance and assuming launch and land heights are equal, theta that maximizes, well, I'm not even going to be able to write that in this space, so I'm going to erase it and say theta that maximizes range is theta equals pi over 4, which equals 45 degrees. So if obviously if you're actually throwing a ball, then chances are you're throwing it from some height that's different than the ground height. But that's a pretty good first order approximation to just assume you're throwing it roughly the same height, and therefore 45-degree angle would be slightly better. If, however, you want to take into account the fact that you're firing it from another height, then what you want to do is shoot it a little lower than 45 degrees because then it's supposed to act like the remainder portion of the trajectory, which is here. So notice at this point, the angle is less than 45, is less than 45 degrees. Whereas right here, it would be 45 degrees if R equals R max. And you can get that just by taking the derivative of R with respect to theta, and you would see that it does work out to be 45 degrees or pi over 4. Any questions on that? I now have Michael, which is a different Michael than I started with, and Sam. Anybody have any questions on what we've done so far?
No, and I switched to my phone. My laptop died.
Oh, is that you? Gotcha. You
Yeah,
signed in a little bit earlier, didn't you?
I did. Yeah,
Okay. And you're Michael with a T on the last name, right?
yeah. I'm the OG Michael.
Okay, cool. Good deal. All right. Well, this is actually it. The only thing that's left in this section is relative velocity. So I'm going to give you a really quick rundown of that, and then I'm going to tell you how to deal with it in relativity because that gives us a neat little side for special relativity. So you'll have some special relativity. So if you imagine a coordinate system like this, X and Y. And if we imagined at any point in, or let's say at the initial point in time, t equals 0, if we imagine the two coordinate systems were in exactly the same place, so that's Y prime and this is X prime, if we waited to some time later, what we would find is that X prime is moved over here and Y prime is over here. And in fact, this is at t equals 0, and this is at t greater than 0, then this distance right here, if we're imagining that the velocity of the frame, actually, I'll just say a v there. If the velocity that the prime coordinate system is moving with respect to the non-prime coordinate system, if that velocity is v, then this distance traveled here is v times t. Because of that, you can say that x is going to be equal to x prime minus, well, actually, I should say x prime. So, for instance, if we had this right here is x prime 1, then this would be x prime 1 plus v times t. So that's the way you combine reference frames that are moving with respect to each other. So you could imagine, for instance, the purple reference frame is the ground, and you could imagine the red reference frame is a Mack truck flying by at 60 miles per hour. Because of that, we can figure out that the velocity is actually given by this formula. The velocity of A as seen by C. Now, I'm going to give it to you in, well, I'll first off give it to you in one dimension, but I'm going to tell you that it generalizes to three dimensions. But the velocity of A as seen by C, that's the way you write that. When you say V sub AC, it's the velocity of C of A relative to C. Now, the way we can work out a formula that will always work is the velocity of A as seen by C is equal to, I take that first subscript and I make it the first subscript in here. So I'm going to say the velocity of A, but I'm going to leave a blank because I need a second subscript to reference what reference frame I'm using. And then I'm going to say plus V. Again, I'm going to leave a blank, but this time I'm going to take the last uh, suffix, or excuse me, the last subscript. That's what I was shooting for. And that's going to be C. So see how the AC matches the outer two subscripts? That's important. The other important thing is the middle subscripts have to match. So this could be B and B. It could also be Q and Q. The main thing is these two have to match. So for a formula, these two must match, and this one has to match, and this one has to match. So that's how you actually find relative velocity. So velocity of A as seen by C is equal to the velocity of A as seen by B plus the velocity of B as seen by C. That's a typical one. Now let me show you what that means. Let's imagine that this is the Earth, and let's imagine there's a spaceship right here. That's spaceship A, and it's moving at, let's say, velocity of A as seen by Earth is equal to positive 4/5 the speed of light. And then I'm also going to say that there's a spaceship B, and the velocity of spaceship B relative to Earth is negative, let's say 7/8 C. What I would like to know is what is, so let me box this off so we know this is a separate example. What is the velocity of B as seen by A? Okay. So this is a case where you're going 60 miles per hour down the road. Someone else is coming towards you at 70 miles per hour down the road. The velocity at which y'all are approaching each other is your 60 plus their 70, which equals 130 miles per hour. That's what you'd expect. That's what we're trying to find out here. But according to our addition of velocities formula, the answer is as follows. Solution. Remember, the suffix rule is what we're using, or the subscript rule is what we're using. So I'd like to know the velocity of B, excuse me, velocity of B as seen by A is the question mark. Notice how I had to understand what subscripts to use for the velocity I'm shooting for. The velocity I'm shooting for is the velocity of B. So that's the first subscript, but I want to know what it is relative to A. So that's the second subscript. So according to our rule for subscripts, velocity of B as seen by A has got to equal the velocity of B as seen by something plus the velocity of something as seen by A. So I need something that matches. When I look up, I see that I have a VBE, so that might be a good idea. So I'll put the E in here, but if I put the E here, that means the E has to go here as well. So that's exactly right. The other rule that has to go with this is something that should be pretty obvious to you. If you are going, let's say, 65 miles per hour down the road northward, and another car is next to you in the other lane and they're going 60 miles per hour northward, then according to that other car, your velocity is 5 miles per hour in the positive direction. Because let's say we both agree that the direction the car is going north is positive. We both have to agree what the positive direction is. That's sort of the nature of the way the systems are set up. The x axis has to point positive in the same direction for both cases. So, if you're sitting in that slower car, you see if you turn sideways, for instance, in the passenger seat, and you watch this car, he's moving from right to left, which is the same direction you're going. You're calling that the positive direction, and you know that he's going 5 miles per hour faster than you. So it's almost like you're sitting still and he's just going by you at 5 miles per hour. So the velocity of the other car with respect to your car is VOY equals positive 5. Now, if you're in the other car, the velocity of y with respect to O is negative 5. So that gives us this neat little rule that Vij is equal to the negative of Vji. In other words, if you reverse the subscripts, you just flip the sign. So that's the extra rule that we need. So if I go to do this, I do have the velocity of B as seen by E. That is, in fact, negative 7/8, excuse me, negative 7/8 C. I do not have the velocity of E as seen by A, but I do have the velocity of A as seen by E. So I just need to replace that with the negative of it. So I'm going to say minus VAE. In that case, I get negative 7/8 C minus 4/5 C. Now, the least common denominator between the two is 8. 4 to 5 does not go into 8. 16, 5 doesn't go into. 24, 5 doesn't go into. 32, 5 doesn't go into, but it does go into 40. So that's going to be 5 times 7 would give me negative 35. And then 8 times 4 would give me negative 32. And then the denominator, of course, is 40. So negative 35 minus 32 would be negative 67. So I get negative 67/40ths C. So the velocity of B as seen by A is negative 67/40ths, which is approximately negative 1 and 27/40ths the speed of light. Now that's technically correct. So that is the actual way that we add relative velocities. But as you know, according to relativity, nothing goes faster than the speed of light. And it turns out if you carry out the derivation for this expression in special relativity, it turns out that relativistically speaking, VAC is equal to VAB plus VBC. But here's the difference. We've got this denominator, and this denominator is 1 plus VAB times VBC over C squared. So if I try to carry this out with this math, we still get the same stuff going on in the numerator. We're going to get specifically, uh, well, actually, I'll do it like this. VBA is equal to negative 35 over 40 C minus 32 over 40 C divided by 1 plus. Now, the VAB and the V, or excuse me, the BE and the VEA is what's supposed to go at the bottom. The VBE is negative 7/8 C, and the VAE we don't have, so we have to use the VEA, which is negative 3/5 C, or excuse me, negative 4/5 C. And then both of those are divided by C squared. So you can see that the C squared cancels out these two C's. And what we end up getting is the top is still going to be negative. Actually, I meant to keep that in green. The top is still going to be negative 67 over 40 C, but the bottom is going to be 8 times 5 is 40. So this would be 40 over 40. That's the 1. And I'm making it way too small. Y'all can't see that. So let me correct that a little bit. Negative 67 over 40C divided by 40 over 40. That's the 1. And then the minus and the minus gives me a positive. So that's going to be plus. But now we have 7 times 4 is 28. And 5 times 4, or 5 times 8 is 40. So we have in the top negative 67 over 40 times C, but in the bottom we have negative 68 over 40. So we end up getting the result is, excuse me, it's positive in the bottom. Sorry about that. So it's 67 over 40 divided by 68 over 40, which becomes negative 67/68 C. Isn't that awesome how relativity just barely makes it smaller than C? All right, that's it. You guys are done. And actually I ran over by about 3 minutes, so I apologize for that, but you're free to go. Remember, you're supposed to have a lab tomorrow at 8 a.m., but we actually have no lab that day, so I won't be signing in or anything. I might sign in just because some people aren't going to see this message. So I might sign in long enough to tell them, hey, I'm not coming. But that's just, we normally leave one day during the test week open in our lab so that we can use that for a testing period. But I made your test happen on Sunday. So you guys should do that on Sunday. You do not have to meet for lab tomorrow. So have a good one. I'll wait here till the last person leaves. So in case anybody has any question, I can answer them, but you're free to go. And we're completely done with chapter 3. Next time we'll start chapter 4. Good luck on your test this weekend.
All right, thank you. Have a good one.
Thank you. You too, Michael.
Lou, can you hear me?
Yes.
I just had a question. Did you see the email I sent to you yesterday for my I set up a time for proctoring.
Oh, okay, gotcha.
Um,
I remember the email coming through to me, but I don't remember. I don't think I actually read it. That might have been the problems. Uh, but yeah, I have. Let's see right here.
there should be just the just me saying that when I'll be taking the test, and I also just forwarded the
Oh, yeah, I got it.
um yeah, I also just forwarded the information they sent me just in case.
Okay, so June
Um,
6th at 9 a.m.
yep.
No problem. Yeah, I'll get that for you, and they'll have the password and everything that you'll need to access it.
Okay.
So you should be free to go there. And good luck. Just remember what I told students was every time you solve a problem, if it's
Hmm.
unless it explicitly says you don't have to show me your work, then you need to show me your work. And you should start with writing variables, assigning them values that the problem gives you, and then write
Okay.
out the unadulterated equation and then
Hmm.
plug in the numbers with the units and then solve it algebraically and show me that. That way I can give you a maximum amount of partial credit if you don't get it exactly right.
Okay.
Okay?
Yeah, I'll I know you put out something about the practice test. I'll probably be doing that
Gotcha.
tomorrow.
Okay.
Um
Yeah, I would do it as many times as you can.
yeah,
You should use that for, but yeah, go ahead.
I'll be I was just yeah, I know you said you were like concerned, so I
Yeah.
was planning on doing it regardless. I just
Yeah, that's just me warning y'all to make sure you do it. So don't worry about it. I wasn't really upset with anyone. I suspected that most people wouldn't be able to get to it yet. But I'd hoped that everybody would have gotten to it beforehand. So that was just me saying, "Hey, make sure you start doing it." I can't express to you how important it is to do the practice test many, many times. You will really get a good feel for how much help that is once you take this first test.
okay. Um and I should, since I'm doing it proctored, there shouldn't be any special things I have to do for respondus. Just you just going through the process basically.
Yeah,
Um
look for when you go there, there might be one
mhm.
with your name in it, because it's a bit of trouble to make it where it has to use Respondus Lockdown Browser and Respondus Monitor,
Mhm.
and then I have to send it to a testing center. So I might just make a separate one and it'll have your name in the title of it, and you just take that one.
Okay. Um I'll see if I can do some sort of test to see if I can get it to work. Because I know my calculus teacher, they had like a little test to see
Hmm.
if you could use Respondus, and that's how I figured out
Oh,
it
good.
didn't work.
Yeah, if you
Um,
can get that, you can cancel that appointment, and they'll give you an extra day to study. That would be helpful for you. So by all means, do that if you can.
yeah, I'll figure it out. But I thank you for accommodating me.
No
I
problem.
appreciate that.
No problem.
Um,
I'll do my best to make it easier for you and all that good stuff. But yeah, let me know whenever you have a problem. I'm really pretty easy to work with. I'm really student centered. I want to help you guys. So let me know if there's anything that bothers you. I'll be glad to help you.
okay. You have a nice day.
All right, you too. Talk to you later, bud.
All right, talk to you
Bye bye.
later. Bye.
All right, so that's it. Hope you have a good day. Bye, everyone.